In this next video, we're going to go through an example of a second order differential equation and solving it using the Laplace transform method. Notice this is a undamped forced harmonic oscillator, alright, and it's got a sinusoidal forcing function, meaning we get a trig function on the right hand side. We could use other methods we've learned this semester, but we're going to use the Laplace transform here, and eventually the Laplace transform will allow us to model certain types of forcing situations which we haven't seen before with discontinuous forcing functions. But let's go through the process using the Laplace transform to solve this differential equation. Alright, so as we've seen in some of our previous work, the idea is going to be to take the Laplace transform of the equation. Alright, for this one we're going to be using the fact that we know the Laplace transform of cosine of omega t is s over s squared plus omega squared. So looking at our example, the number omega for us is 3. Alright, so first step being, okay, let's apply the Laplace transform. Alright, so that's going to say it's the Laplace transform of the second derivative. Again, Laplace transforms are linear. It's a linear transformation, meaning we can apply that term by term. Alright, so it's going to be 4 times the Laplace transform of y, and that's going to equal 5 times, on the right hand side, the Laplace transform of cosine of 3t. Okay, now the other fact that we're going to be invoking here, and then I'm going to start to write this all in terms of capital Y. I'm going to go over to my table once more and come back here. So we're going to have to use the fact for cosine, and then from our previous work and other videos, we're going to use the fact at the bottom here that the second derivative, Laplace transform of the second derivative, is s squared times Laplace transform of y minus s times y of 0 minus y prime of 0. So we need to apply that fact for this term. Alright, for the first term. Alright, so again, we're going to do s squared times, we could do L of y, but just, I think I'm just going to write capital Y just for a little bit simpler. So capital Y is the Laplace transform of little y of t, the function we're looking for, and then it's minus s times y of 0 minus y prime of 0. So that's the first term, turns into those 3. Then it's going to be plus 4 times the Laplace transform of y, little y, which is big Y of s, is then going to equal 5 is the constant factor that comes along for the ride. For cosine, it's s over, just be careful, my 5s sometimes look like s's, s over s squared plus omega squared. Well, omega's 3, so we're going to get plus 9 there. Okay, and now we need to enforce the initial conditions. So we're going to substitute in what y of 0 is equal to. That's equal to 1. And y prime of 0 is also equal to 1. Alright, so substituting those two things in, and then let's also at the same time combine these like terms on the left side. We get s squared plus 4 times capital Y of s is, and then minus s minus 1 is equal, we can write this here as 5s over s squared plus 9. Okay, now we need to add over, because our goal here is to isolate the Laplace transform. So we need to next add over s, add over 1 to both sides, so add over s plus 1. Okay, and just rewriting this again, we get s squared plus 4 times capital Y of s, Laplace transform of little y, and that's going to equal then 5s over s squared plus 9 plus s plus 1. Alright, next, isolate, we need to do the division. Alright, so what we're going to do is multiply both sides by 1 over s squared plus 4, which is equivalent to dividing both sides by that quantity. So each term, we got to do that to each term on each side. Again, that's like dividing by s squared plus 4. Doing that, we now have got capital Y of s isolated. It's 5s over, I'm going to write the s squared plus 9 term first on the bottom, or factor first on the bottom, s squared plus 9 times s squared plus 4, and then plus, this will be s plus 1 over s squared plus 4. Okay, now eventually we need to go through and find the inverse Laplace transform, which will come out in terms of sines and cosines, but for us to do that, we're going to need to do a little bit more algebra. Let's add these fractions together first, because we don't have the same denominator. Alright, let's combine this as one term, and then we're going to apply partial fractions after that. Okay, so we need to get the same denominator to add these fractions, so that's going to be s squared plus 9 times s plus 4. So we need to, for the second term, we need to multiply the top and bottom by s squared plus 9. Alright, now we can now put that all over one fraction. So capital Y of S is going to equal 5s plus s squared plus 9 times s plus 1, all divided by the common denominator, s squared plus 9 times s squared plus 4. We want to leave the denominator in factored form, right, because we want to split that into partial fractions. In the numerator, let's go ahead and multiply this binomial out and combine some of the terms together. And that's going to give us that capital Y of S will equal our highest, so our denominator is going to stay exactly the same. Okay, that's going to be the same. It's going to be s squared plus 9 times s squared plus 4, right in the bottom. And then we'll have in the numerator, we're going to have s cubed, and then the s squared term would be just one s squared term. We're going to get 9s plus 5s, that'll give us 14s, and then 1 times 9 will give us 9. Okay, so there is the Laplace transform. It's equal that's the function of s it equals. Now what we're going to do is to find y of t, which is going to be the solution of this differential equation, we need to find the inverse Laplace transform of that. For us to be able to do that, what we need to do is split this up into its partial fractional decomposition, meaning something over s squared plus 9 plus something else over s squared plus 4. And therefore we'll be able to see that that's going to be resolved like in the previous video where we practiced finding some inverse transforms in terms of sine and cosine. Now, what do these numerator terms turn into? Well, it's not just going to be a and b. Alright, from your previous work in Calc 2, if you have an irreducible quadratic factor, which we do in the denominator there, s squared plus 9 doesn't factor in terms of linear binomial factors, it's a times s plus b. It's got to be a linear factor on top. And likewise for the other one, we have an irreducible quadratic factor, so we need a linear term, we need a linear numerator there, cs plus d. Alright, and like in our previous examples, we need to now clear the fractions out and multiply by multiplying both sides by the LCD and then equate coefficients. Alright, so I'm going to jump to the next step. If you multiply each side by the LCD, which is s squared plus 9, it's going to completely cancel the denominator on the left side, leaving us with s cubed plus s squared plus 14s plus 9. On the other side, well, that, whoops, I jumped up a little bit on me there, sorry. That numerator, as plus b, the s plus 9 will cancel when we multiply by the LCD. We'll be left with s squared plus 4, and vice versa, we'll be left with an s squared plus 9 factor here. Alright, now I'm going to multiply that out a little bit to write the system down. I might just tell you what the coefficients are and you can double check it, but now it's just a matter of distributing all of this out, right, and combining like terms together. Alright, so a little bit of writing to do here. So copying down my left side, and then what are we going to get? We're going to get as cubed plus bs squared plus 4as plus 4b, and then the next one's going to be cs cubed plus ds squared plus 9cs, and then plus 9 times d. And then we just want to combine our like terms. We've got s cubed terms, right, and we've got s squared terms, we've got s terms, and then the last types are constant terms. Alright, so factoring or combining like terms there, what do we end up seeing this is equal to? We've got something times s cubed, right, plus some coefficient times s squared, plus a coefficient times s, and then plus a constant term. And what does that turn into? With our cube terms are a and c, we get a plus c. Our squared terms are b plus d. Our s terms are 4a plus 9c. And then our linear term, or constant coefficient terms are 4b plus 9d. Just going to clean that up a little bit. Our S terms were a 4a plus 9c, s, and then it was 9d at the end there. Now, like in our previous example, we need to equate coefficients. So the coefficient of s cubed on the left is 1. It's got to equal the coefficient of s cubed on the right. So that's going to say 1 has got to equal a plus c. Our coefficient of s squared on the left is 1. So that's got to equal our coefficient of s squared on the right, which is b plus d. And the coefficient of s has to equal the coefficient of s on the right. And the constant term on the left has to equal the constant term on the right. Okay, and now notice what this does. I'm going to just say what the answer is to this, what it is for A and B and C, but notice this actually decouples kind of nicely. You get two equations that only involve A and C and two equations that only involve B and D. Now if you go through and solve this, I'm just going to tell you what the results are. You can double check it for me. A comes out to be -1, and correspondingly you're going to be solving the system for C. You're going to get C is going to come out to 2. The B and D system, you're going to get D is equal 1 and B is equal 0. Alright, that's just the way that works out, as you can check for me. Okay, now let's apply that. So what did we have before? We had capital Y of S was equal AS plus B over S squared plus 9, and then CS plus D over S squared plus 4. Now we're going to plug in A, B, C, D as we found up above here. Okay, so plugging in here, we end up getting just -1s plus 0 on top of this one. Alright, and then we get 2s plus 1 over s squared plus 4 here. Okay, so now our goal is going to be to invert. Okay, so for this one, like in the previous video, we're going to need, for the second term, we're going to need to divide this whole denominator, s squared plus 4, up into each term and split that up. For the first one, this one we can just pull the negative off, and that's s over s squared plus 9. That one we can recognize right away. For the second one, we're going to rewrite this as 2s over s squared plus 4 plus 1 over s squared plus 4. Okay, and then we'll just do one more rewrite and we'll have it. We can, for the second term, we'll just pull the 2 off. For the next term, we really want a 2 to be in this numerator. So we need to force a 2 to be there. And we can do that by multiplying the top by 2 and then dividing the bottom by 2. For the second term, we can just pull the factor of 2 off. It'll be 2 times s over s squared plus 4. For the second one, we want it to be 2 over s squared plus 4, because then we can recognize that as the transformation of sine of 2t, but we don't have a 2 up there, so we have to compensate by multiplying it by 1/2, right, as we've seen in our previous work. Now we can say, alright, via the Laplace transform, what do each one of these terms turn into? Right, well, this one turns into little y of t, right? Little y is related to big Y via the Laplace transform. The first one is exactly the cosine of 3t, plus, now we're going to get the 2 factor coming along for the right. S over s squared plus 4 is exactly cosine of 2t. Right, the one with the s on top relates to the cosine, so it's kind of opposites. Cosine starts with c, but we have the s on top of its transform, so it's cosine of 2t, and then we get the 1/2 come along for the right, and this one doesn't have the s, so that's the one that deals with sine, and our omega value is 2 there. Okay, so that is the solution of that initial value problem. Okay, again, we could have done that using the method of undetermined coefficients, as we've learned before. This is an alternate method for us.